Our next speaker is Preeti Bhandari, and he's going to talk about variable range hopping in a non-equilibrium steady state. What do you?
Good afternoon, everyone. Thank you, organizers, for giving me the opportunity to present one of my recent papers, variable range hopping in non-equilibrium steady state. So first, let me tell you the model Hamiltonian which I'm using to study the problem. It's called the Coulomb glass model. So as in the Hamiltonian, you have some disorder in the system, that's the on-site disorder, and the Coulomb interactions. So this Hamiltonian is interesting when the disorder and interactions are comparable. So very easy way to explain is that if you just have Coulomb interactions, the electrons want to be as far from each other as possible. But then you have these on-site disorders, which might pin the electron to a specific positions. When they are competing, then you have this glassy-like behavior in the system, which is seen in many systems. So you have rugged energy landscape. Now, one of the key feature of this Coulomb glass model is this Coulomb gap. If you don't have Coulomb interactions, when the Coulomb interactions are present in the system, your density of state changes and you have a gap around the Fermi level. So there is separation of density of states just because of this Coulomb interactions. And because of this, there is also, it affects your transport properties. So previously, in the absence of Coulomb interactions, we had the Mott law, which suggests that the conductivity is related to temperature by T 1/3 law. And then there was this Effer-Shavorsky law considering the Coulomb interactions, and there was a modification that it is now T half law. So now the motivation of my paper, it was based on an experiment by Professor Zabiovadew. What he did was he took an indium oxide and he first equilibrated the sample. He calculated the density of state and conductivity of that equilibrium system. So again, like I said, there is a gap in the density of state, and then there was some conductivity corresponding to the equilibrium system. Then what he did that he exposed that system to IR radiations. Okay, he kept the temperature same, but he exposed the system to IR radiations. So the energy first increases and then he reaches some steady state, which he calls a non-equilibrium steady state. And then he again calculates the density of state and conductivity. The interesting part here is that he sees a significant increase in the density of state, that means the filling up of the gap. But according to him, the conductivity did not change much. There was just, the increase in conductivity was 2.8%. So what we tried was, we tried to mimic the experiment via a simulation. So first we did a Monte Carlo, equilibrated the system, calculated density of state and conductivity. And then to mimic this non-equilibrium steady state part, what we did was, we deliberately excite the system. So for example, what we call a Kawasaki dynamics. We take a spin up and spin down and we exchange it so that there is an increase in energy. And then we relax via the normal metropolis system. And then we also calculate the conductivity by applying some small field. So the parameter which we are now calculating is the effective temperature. Now we know that when the system is in equilibrium, you calculate any observable, density of state, conductivity, Fermi Dirac distribution, they'll all correspond to a single temperature, which is a bar temperature T. But now in case of this non-equilibrium state, what we find is, for example, we calculated density of state and conductivity, and we see that each observable corresponds to a different effective temperature. So the procedure to calculate the effective temperature is that I know what is the relation of density of state and temperature at equilibrium, which is my solid line here. So red data is the equilibrium data. And then I do my non-equilibrium study, I get some density of state. This is the density of state at the Fermi level. So I see what is the density of state there, and I keep my effective temperature as a free parameter. So how that density of, what temperature corresponds to this particular density of state, that's my effective temperature at that particular excitation. Similarly, I did for my conductivity also. And what I find is that for the non-equilibrium steady state, it cannot be characterized by one single temperature. There are two different, effective temperature corresponding to density of state and effective temperature corresponding to conductivity were different. Now if I map it to what experiment was done, like I first said, when you are in equilibrium, so the dashed line here corresponds to the equilibrium temperature. Okay, so I considered three different temperatures, beta 20, beta is inverse of temperature. So I considered beta 20, 40 and 80. So these dashed lines are those corresponding temperatures. And initially, so here these different points corresponds to different relaxation steps. So I tried to make my simulation a lot more general. He considered one single intensity. I considered different relaxation step. That means I excite, let's say I excite one step and then I relax it for one step. That corresponds to one relaxation step, the first point here. Then the second point corresponds to, I let it relax for 10 relaxation steps. So longer my relaxation step, closer the system will be to its equilibrium value. So you can see for beta 20, it reaches its equilibrium, and there both density of state and conductivity corresponds to the same point. So system reaches equilibrium. And for beta 80, which was my lowest temperature, the system, within the window of time I did my simulation, the system never reaches equilibrium. And hence, the two observables lead to two different effective temperatures throughout the simulations. So we did get the results which was observed in experiment, that effect on density of state was more. So the effective for density of state was higher than what we get in conductivity. But our results, quantitatively, it was not as same as the experiment. And when I had a discussion with the experimentalist, Professor Zavi, he told me that what we calculate in simulation is density of states. It's measuring the energy. So density of state is distribution of energy. But what the experimentalists do is, so DOS and memory dip is, they have similar proportional, but there is one fundamental difference. What experimentalists are calculating is quantity called charge. So that can affect the results. And another possibility is that in my simulation, I'm not considering the quantum effects, which can be a reason why the conductivity and DOS might be having much more difference. But within this simulation, which I was doing this setup, I could also look into another model, which is called the hot electron model. Now, broadly speaking, hot electron model is that the electrons, they thermalize themselves. They don't need phonon assistance. In equilibrium, at low temperature, we know that electrons need phonon assisted hopping because they don't have sufficient energy. But in a hot electron model, you provide some external, you drive the system externally by providing light, voltage, or electric field. And now the electrons, like the word says, hot electron, that means the electron has its own energy, and they can do the lowering transitions themselves, and they don't need the phonon transitions there. So in this case also, the transport mechanism is same. They still follow the Efroshev-Sky law, but the only difference is instead of bar temperature, you have this effective temperature there. So within our setup, we studied this hot electron results as well. So the solid line is the conductivity, Efroshev-Sky conductivity at equilibrium. Okay, so this is the equilibrium data. Here what I'm trying to show is that for the three different temperatures I studied, beta 20, 40 and 80, how the system goes from phonon assisted hopping to phonon less hopping. So for beta is equal to 20, my system was not very far away from the equilibrium, and the data still overlaps with the equilibrium line, which means there is still some phonon assisted hopping happening in the system. On the other hand, the other extreme, beta 80, there you can see that the two lines are approximately parallel. So what is happening is you still have the VRH happening, but your intercept is small now. So here what is happening is, in equilibrium you have delta E greater than 0 transition, delta E less than 0 transitions, and they are equal. At beta is equal to 80, where I am having phonon less hopping, there only delta E less than 0 transitions are dominating. The delta E greater than 0 transition are suppressed, and we have phonon less hopping here, and beta 40 then shows a transition between phonon assisted to phonon less hopping. This is just what I explained, and this is the conclusion of my paper, that we replicated the experiment and we also explained the hot electron model via simulation setup.
Thank you. We will take, because of time constraint, we will take only one or two questions.
short question. So, can you tell me what was the effect of the localization length bits?
Yes. So when I'm talking of the
what is the prefactor? How does the temperature? How does the prefactor depend on temperature in your calculation?
Basically, the prefactor here is telling that if you have both delta.
Yes, but in different calculation, you get different temperature dependence for the prefactor. So what do you get in your calculation?
Sorry, I didn't.
In the prefactor of the Efroslavsky scaling, you get different temperature dependence on how you do the calculation. So in your case, is the prefactor temperature independent?
Yes. My temperature was fixed. The simulation was done. That means in experiment also the temperature was fixed. You are giving energy to the system in a certain way. In my case, I am deliberately the excitation and the relaxation step. Longer relaxation means closer to. So it is not the temperature is not varying in the system. It's just the relaxation steps which I am varying.
And what about the localization length?
Localization length was we want variable range hopping, so it was large. If I keep it small, then it will be activated hopping, which I don't want in my system right now.
Okay, thank you.